Alright, so now I'm going to perform stability analysis for this explicit method for solving this parabolic PDE. And the way we're going to approach this is we're going to write this update in matrix vector form. Okay, so we'll write the update in matrix vector form. Okay, so let's call the vector of data Vj. So this is V1j all the way up to Vnj. All right, then I can write the update as Vj plus 1 is equal to A times Vj, where this A matrix is the following matrix. It has a diagonal which is 1 minus 2s. And then the upper and lower ones are s. Okay. And then I'm going to deal with the boundary data by specifying that the boundary values are 0. So I'm going to consider the case where A of t equals to B of t equals to 0. Right? So this is actually the entire thing then. So you don't have to worry about the heat that's like associated with the boundary coming in here. Okay. So now it's like the way you can analyze this, it's like can go in a variety of ways, right? The first of which is that so the first argument is based on the observation that the temperature in the bar goes to 0. It's like as time goes to 0. Sorry, as t goes to infinity. Okay, because the ends are maintained at temperature 0. Okay, so along the lines of what we had done before, it's like when we look at stability, if the solution is going to 0, it's like you would like ideally again that your numerical method it's like exhibits the same property, that the numerical solution goes to 0 as time goes to infinity as well. Okay, so we want the same to be true of the numerical solution. Okay, and then we know that by this recurrence relationship that Vj is equal to A Vj minus 1 is equal to A squared Vj minus 2, which all the way is equals to A to the j V0. Okay, so if you want Vj to go to 0, it's like as j goes to infinity, right? Then there are sort of results which say that so if the limit, okay, well I should say the following equivalent, right? Right. The first one is that if you look at the limit as j goes to infinity of a to the j v equals to 0 for all v, then this is equivalent to the statement that the spectral radius of A is less than 1. Okay. All right. So again, it's like what basically is happening is that if you want to look at the special case, it's like where you have boundary data, it's like where the temperature is set to 0, it's like on both ends, right? And then what happens is, and you want to mimic this property that the continuous solution, it's like decays to 0 as time goes to infinity, then what has to happen then is that, again, this Vj has to go to 0 as j goes to infinity for all initial value v0. That's basically saying that that's this condition here, and this condition is equivalent to the spectral radius of this matrix A being less than 1. Okay? All right. So that's the condition which we need to have. So the net effect is that I want to choose okay, so this matrix A is equal to 1 minus 2s, 1 minus 2s, s, 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 0, 0, right, and s is equal to k over h squared. Okay, I want rho of A to be less than 1, the spectral radius to be less than 1. Okay. All right. So I want to choose S such that rho of A is less than 1. Okay, so another way to see this, so condition same condition. Without sort of appealing and like to this physical intuition about what the solution looks like, is to look at round-off error. The effect of round-off error in the numerical computation. Okay, so say we introduce sort of round-off error by sort of replacing v0, right, with v0 tilde. Okay. So then the method will use this, it's like we'll sort of give basically vj tilde, which is a to the j v0 tilde. Okay, and the error is given by vj minus vj tilde, which is a to the j v0 minus a to the j v0 tilde, right, which is a to the j v0 minus v0 tilde. So basically what you want is, you don't want this sort of small error introduced by round-off to grow, right? So you want the error, the contribution, let me rephrase that, you want the effect of round-off error stay bounded. Or decay. So again, this gives the condition that the spectral radius of A is less than 1. Okay. All right. So, okay. So let's now try to determine the condition on this. All right. So in order to get the spectral radius of this matrix, you have to determine the eigenvalues. Okay. So let's see what happens. So I will state without proof, it's like what the eigenvalues are. And then from that, it's like we can determine what the spectral radius is and what conditions on K and H needs to satisfy in order for the method to be stable. Okay, so the eigenvalues of A are given by lambda j is equal to 1 minus 2s, 1 minus cosine theta j, where theta j is equal to j pi over n plus 1, and j goes between 1 and n. Okay, so for rho of A to be less than 1, right, we require that this whole range is between minus 1 to 1. So this is true if and only if S is less than 1 over 1 minus cosine theta j. Okay, so since S is positive, right, which is sort of the choice here, K over H squared, all right, that's a positive number, all right, the greatest restriction on S occurs when cosine theta j is equal to minus 1. And, you know, it's like, and when, so because theta j is approximately pi when j is equal to n, right, especially for n large, right, we're just going to require that S is less than or equal to 1 over 2. So we'll require that S is less than or equal to 1 over 2. Okay, so the stability condition is that S, which is equal to K over H squared, right, is less than or equal to 1 over 2. Okay. So the problem, of course, is that the problem with the explicit method, of course, is that this sort of imposes a very severe time step restriction. This is a very severe time step restriction. automatically when h is small. Okay, so h is the spatial mesh size, right? So if the spatial mesh is small, you take the square of it and you have to multiply by half, and that's the limit on how fast, how large a spatial step you can take. So this is a very restrictive condition. Okay, all right. So so in the textbook, it's like this discussion of how to derive the eigenvalues. It's like of a tridiagonal matrix. I'm not going to go into that, but that's sort of where you might get sort of these eigenvalues from, and from there you can infer the spectral radius. It's like of the matrix A, okay? Because the matrix A is tridiagonal, as you can see. All right, so in any case, it's like, so that's saying that, well, on the plus side, it's like the explicit method is very, very easy to implement. The disadvantage is that when you have sort of small spatial meshes, when a very fine spatial mesh, it's like you have to take a very, very small time step, okay? So the next thing we'll study then are these implicit methods for doing parabolic equations, and the hope there is that it allows you to take larger step sizes without violating a stability condition. So let me just stop here for now.